Barry from Brooklyn College. I just walked out of my multivariable calculus class. It's currently around 8 o'clock. And today we learned about definite double integrals, not like there's an indefinite version. So double integrals are essentially what happens, they're analogous to single variable definite integrals. It's the volume under a multivariable surface. So the definition, very similar to a single variable integral, is based in Riemann sums. It's basically like in a single variable integral, you take those small rectangles that have the height of the function at a certain value, and you make their length smaller and smaller until it looks like a continuous curve instead of jagged rectangles. It's a little hard to understand what I'm saying if you've never seen Riemann sums before, but if you've taken calculus, you'll definitely understand. And then it's like that, but instead of lines, instead of rectangles, you have rectangular prisms with different dimensions. So you're taking these rectangular prisms that all have the height or z dimension of the function at a certain point, and the x and y dimensions approach 0 as you approach the true volume under the surface, or the true double integral of the function. So we usually don't do things by the exact definition, just like kind of like the single variable derivative, or the multivariable derivative for that matter. There is a very well-defined definition of the derivative that uses limits. The limit is h approaches 0 of f of x plus h minus f of x over h. And honestly, it's not that hard to visualize, but the problem is basically no one uses it for 99.999% of derivatives that you're going to do. Only the very simplest ones, the ones that require like the power rule or something, can be done practically with that, without knowing some sort of random trigonometric identity. So, similarly, we use a similar trick, but it's not too far off from the original double integral. What we really do is we try to take the integral first with respect to y, treating x as a constant. So it's like you have this curved volume, and then you're just taking the volume of the area of one cross section of it, or its cross sectional area. Oh, would you look at that? That's the 8 o'clock bell. So you're taking that cross sectional area at a fixed x and a changing y, and then what you do is you kind of repeat that, but for x instead. So you take that cross sectional x with a fixed y. So yeah, that's about all I have to say for multivariable integrals. Thank you everybody for watching.
Say something about your biggest thing tomorrow.
Oh yeah, the AMC 12/8/2023 is tomorrow. And yes, I know the old problems got leaked, but they've written a new test. So wish me good luck and see you soon. Bye. Alright, let's go. Have a good day. Bye. Yeah. See you.